Hello, I welcome you all to this another interesting screencast. And the problem reads: determine the normal force, shear force, and moment at point C. Then I'll say and draw the shear force diagram and bending moment diagram. All right. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have triangular distributed loading on a simply supported beam. Let's draw the free body diagram. At A, we expect AY, and then also expect AX. Then at B, where we have the roller, we only expect BY. Right. Let's find the equivalent force for this loading. So we can have just a single equivalent force at the very tip where we have the maximum. Let's call it FEQ. This is going to be equal to the area under the loading diagram, half times the whole length, which is 6, times the height, which is 9. And therefore this gives us a half by 63, 3 by 9 is a 27. All right. So let's apply the equations of equilibrium. So we have summation of moments about point A equal to 0 and clockwise being our reference. What do we have? We have a minus 27 times the lever arm 3 plus by times 6 equal to 0. A by therefore is going to be equal to as minus 27 by 3 divided by 6. So we expect a 13.5 kilonewtons. And then when we look at this beam, it is symmetrically, there is symmetry both in the geometry as well as the loading, and this makes the problem much simpler. So we have by equal to 13.5. We expect ay also to be 13.5, right? So summation of forces in the y direction equal to 0. You have ay plus by minus 27 equal to 0. Since we already found what by is, so let's find ay. Ay is just going to be equal to a 13.5 minus 27, and is still a 13.5. And summation of forces in the x direction is equal to 0. And therefore our ax is just going to be equal to 0. Okay. So we are being asked to find the internal forces at C. So let's make a section. Here we have the left hand side and the right hand side. Which one are we going to use? We are going to use the left hand side. All right. So there we go. We have something like this. At A, let me indicate these loads there. We have 13.5 and also 13.5. At A, we have a 13.5, and then we have this triangular load like so. Okay, and this maximum point is a 9 kilonewton per meter. This point is C, and this whole length is 3 meters. We have there a VC, we have a moment MC, and we have a normal force NC. So let's find this equivalent force from this distributed force, and we already know what it is because this is symmetrical. We expect it to be equal to 13.5. Okay, and it is stationed at this distance here. This distance here is equal to, this distance is equal to 1/3. This distance is equal to 1/3 of the length 3, which is therefore equal to 1. Okay, remember centroids of triangular areas. Okay, this one there is equal to half times 3 times 9, and what do you have? You have 0.5 by 3 by 9, which is a 13.5. Okay, so then let's start applying the equations of equilibrium. Summation of moments about point C equal to 0 and clockwise being our reference. What do we have? This is kilonewtons. What do we have? We have a minus 13.5 times 3, a negative, and then we have a plus 13.5 times 1, then plus MC equal to 0. And therefore our MC is going to be equal to, that's minus 13.5 by 3 plus 13.5 by 1. So expect MC to be equal to 27 kilonewtons meters, right? Yeah. Let me minus 13.5 times 3 plus 13.5 times 1. Okay, that's 27. Okay, so let's draw a boundary there. Let's draw a boundary so that we find out, we also calculate for the shear. So summation of forces in the y equal to 0 going up in our reference. What do we have? We have a 13.5 minus 13.5 minus VC equal to 0. Shear there is just going to be equal to 0 kilonewtons. And it makes sense. And that's the very point where we are going to have maximum moment. And then we have finally summation of forces in the x equal to 0. And then what we have? We don't have any loading, therefore the normal force is equal to 0. So we found the moment. Okay, and we found the shear. And we found the normal force. Alright, so now what we need to do is now to draw the free body diagram. To draw the free body diagrams, and we are going to use these two differential equations, which you are already aware of. So the rate of change of moment with respect to x is equal to shear, and therefore moment is equal to the area under the shear diagram or the shear loading. And the rate of change of shear with respect to x is equal to Q, which is the distributed load, and therefore shear is also equal to the area under the load diagram. Right. So let's work on this problem. Like I said, this problem is symmetrical about this axis. Okay, this axis I've just drawn. All right. So we expect the moment to have the same mirror image about that axis, while the shear is going to be the same, but it is going to have different sign. Okay. All right. We have positive, we have negative, positive up, negative, and this is the shear force diagram, and this is the bending moment diagram. Great. Okay. So what do we have at A? We have a 3.5, 13.5. So we expect this to go up like so, up to somewhere there. So, and then when it reaches there, this point here, we are calling it a 13.5 kilonewtons. So our load Q is negative and increasing. Okay, it's negative. Okay, and it is increasing. Okay, it's increasing from A to C. So it's negative and it is increasing, right? From 0 to minus 9 kilonewtons per meter. And then therefore we expect the slope of our shear diagram dvdx to be also be negative, okay, and it will also be increasing. All right. So expect the slope of the shear diagram to be negative and increasing. And because of symmetry, it will be much easier to work out the other one, but I'll still go ahead and do all the explanation. So from here, like we said, we expect the slope of the shear diagram to be negative and increasing. So let's find the magnitude up to C. What will be the magnitude up to C? So we know that shear is equal to the area under the load diagram, okay, integral of Q dx, which is just equal to the area half by 3, the length, then by 9. And this gives us a 13.5, okay, right? So this is negative. We don't need to forget that this is negative because the load is negative. This load is negative, therefore this shear is negative. So we have a positive shear from A there, which is 13.5, then minus 13.5, the one that we just calculated, and therefore this gives us a 0. So which of the curve, again, I'll draw two between this one in terms of now the slope that is negative and increasing, between this one, Oh, come on. Let me put between this one and this one. Okay. 1 and 2. Which curve has a negative? Both of them, of course, have negative slope, but which of the two has an increasing slope? Between 1 and 2. Which one? Of course, it is 1, right? It is 1. Of course, it is 1. 1 has an increasing slope, a negative increasing slope. Okay, so we'll go with 1. Great. So we'll come up to the very middle here. Let me just, so this slope will come like this. And when you look at the loading, it is a polynomial. It's been governed by a polynomial of degree 1. It's a linear equation. So you expect the shear equation to be quadratic, right? Or polynomial of degree 2. So it will be something like that up to there. All right. I drawn it properly. Yeah, it cannot be better than this. It can, I know. Something like that. All right. So there we go. And then, of course, at that point it is 0. So this is the curve that will govern the slope. All right. So let's do some more work. So what do we have again? From C to B, we have the shear that is negatively decreasing from 9 to 0. So the load is negatively decreasing. So it's negative. The slope is negative, and it is. The loading is negative and it is decreasing, which is this distributed load is negative and decreasing, okay, from negative 9 to 0. So we expect the slope of our shear force diagram dV dx to be negative as well as decreasing, right? And what's the value? This area is the same as the other one, right? It's the same as the other one. So this one is also going to be the area under the loading diagram, mind you, is negative. This is also just going to be equal to minus 13.5. Okay, so the slope here, which is negative and decreasing, is something like this. Okay, great. I think I've just drawn it properly. Let me draw it again. Okay, something like that. Okay, now it's difficult to draw this nicely since this is a quadratic. Alright, okay, something like this. So when it reaches this level here, this point here is a 13.5 kilonewtons. And then at B, we have finally that 13. So we have a minus 13.5 plus 13.5, which gives us a 0. So it will close. So this closure, you expect a closure to this business. Okay, you expect a closure like so. Great. So this has closed. So this is positive, this is negative, and both of them have the same magnitude because of symmetry. Okay, these have the same magnitude. All right. So let's look at the bending moment diagram. The bending moment diagram. There we go. Let me delete this stuff here. And for moment, we expect moment to be quadratic of degree 3. Okay, of course. So let's look at the shear. The shear here is the shear V is positive and it is decreasing, right? You see, from 13 to 0. and therefore you expect the slope of our moment to also be positive, okay, and it will be decreasing, right? And what's its magnitude? This magnitude here, so this is quadratic, okay, and so we need to find the area under this curve. All right, so now we need to find the area under this curve. So our moment is going to be equal to integral of v dx, okay, and at this midspan, of course, uh, we already know what the moment is, okay, because we need an equation here for shear, all right, for us to integrate this quadratic, quadratic equation. So if we wanted the actual formula, then we could write this from principles, do a section x there like so v, then we have a moment like that, right? And then at this point here we have what we're going to call q, okay, so q, and then here we are going to have an equivalent force we are calling f, okay, and f we know is position from this point there, it is 2/3 of x. All right, so now this q is equal to, this q governing this line here is equal to writing it in the form y is equal to mx plus c. So the gradient there is going to be the difference in the y, which is 9, divided by the difference in the x, which is 3, and then we have an x, so therefore this is going to be equal to 3x. So this is the equation that governs the distributed load from A to C. So finding f, so this q is equal to 3x, and therefore f is going to be equal to half times q, okay, times x, okay, which is therefore equal to just a 1.5 x squared. All right, then summation of forces in the y direction, we are going to have a 13.5, okay, so this is summation of forces in the y direction. So let me write here, so summation of forces in the y direction, so we have a 13.5 plus and then minus f, which is just a 1.5 x squared, and then minus v equal to 0. Then v is equal to 13.5 minus 1.5 x squared. Therefore m is equal to, like we said, integral of v, we are integrating from 0 to 3 of 13.5 minus 1.5 x squared dx. So this gives us a 13.5 x, if we integrated this, minus 1.5 x to the power 3 divided by 3, and we are evaluating it from 0 to 3. So this therefore gives us 13.5 times 3 minus 0.5. 1.5 over 3 is just 0.5 times 3 cubed. So this gives us a 27, okay, kilonewton meters. So this is the moment from A to C, all right, and we said its slope is going to be positive but decreasing. All right, his slope will be positive but decreasing, right? Okay, so since the shear is a polynomial of degree 2, we expect the moment to be a polynomial of degree 3. All right, so let's draw it. So it's going to be like this up to there. This is positive but decreasing. It has positive slope but decreasing up to here. All right, so this point here we said is a 27. We can write it down, 27 kilonewtons. And then from there, like we said, this is symmetrical, so we expect the same curve also to be the same like the other side. This side, it will have a negative slope but increasing. So we are done, and this is about it. And if the video was helpful, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.